400,000 tons of solid basalt vanished from an Indian mountainside, leaving behind the world's largest monolithic temple carved from the top down. The official story claims ancient builders did this in just 18 years, by hand. Yet when you run the numbers, the timeline breaks reality: 5 tons of rock per hour with zero margin for error. If the math is impossible, what secret method did they use? This investigation pits history against hard evidence, and the truth may rewrite everything we know about ancient engineering. At the heart of Maharashtra, an immense stone mass rises from the Ellora plateau, a temple not built but revealed. The monument known as Kailasa, Cave 16, stands as the world's largest monolithic structure, cut directly downward from a single basalt cliff. Its dimensions defy ordinary construction, stretching nearly 300 feet in length, 154 feet across, and soaring more than 100 feet high. The entire complex, including its bridges and colonnades, was not assembled block by block. Every pillar, every sculpted surface was freed from the mountain itself. Mainstream accounts credit this feat to King Krishna of the Rashtrakuta dynasty, who reigned from 756 to 773 CE. His name appears in copperplate grants and later chronicles, linking his patronage to the temple's creation. Yet the historical record is silent on the details that matter most. No inscription inside Kailasa or in the Rashtrakuta archives specifies when the work began, how many years it spanned, or how many hands shaped its stone. The oft-repeated claim that it was completed in 18 years circulates in modern guidebooks and popular articles, but finds no support in the original texts. What survives is the physical evidence. The temple's footprint dwarfs the Parthenon in Athens, its volume nearly double that of the Greek icon. Unlike the Parthenon's orderly blocks, Colossus' mass was subtracted, not added, requiring every cut to be planned from the summit, with no possibility of undoing a mistake. The Shikara, the temple tower, rises in perfect alignment above a courtyard cleared of hundreds of thousands of tons of rock. Bridges of solid stone link the sanctuary to outlying pavilions, each connection requiring flawless anticipation of the temple's final form. Archaeologists and epigraphists can point to the names and the era, but the logistics remain unrecorded. What is certain, the monument's scale, the hardness of its basalt, and the absence of any ancient blueprint or construction diary. The official story offers a name and a legend. The stone itself offers only its silent, impossible mass. Begin with the numbers. The most widely cited estimate for the mass of rock removed from Kailasa is 400,000 tons. Except, for the sake of argument, the traditional construction span of 18 years found in guidebooks. Divide 400,000 tons by 18 years. That equals 22,222 tons per year. Break it down further. With 365 days in a year, the daily rate climbs to just over 60 tons of basalt carved away every single day. There is no accounting here for monsoon seasons, religious festivals, or the inevitable delays that come with stonework. The arithmetic assumes relentless, uninterrupted labor every day, year after year. Take it one step closer. With no artificial lighting, ancient crews would have worked in daylight, at best a 12-hour shift. 60 tons divided by 12 hours equals 5 tons per hour. 5 tons per hour is not just chipping at a surface. It is the equivalent of clearing a fully loaded dump truck of basalt every hour, using nothing more than iron chisels and hammers. For perspective, a modern construction site would assign heavy machinery to this task. Here, the official story expects hand tools to match that rate. Over the course of the project, that is 16,000 dump trucks worth of stone, all hauled out from a single mountain. The numbers do not leave room for planning, for error, or for the slow, careful work of sculpting statues and reliefs. They do not account for the complexity of carving bridges in solid rock or the need for constant layout checks to avoid catastrophic mistakes. The excavation rate implied by these figures is not just ambitious, it is mathematically unforgiving. The contradiction is now set. The legend of 18 years collides head-on with the physical reality of the mountain. Carving a temple from the top of a mountain means every decision must be final. The first cut at the summit sets the fate of everything below. To begin, workers had to outline a U-shaped trench at the very top of the basalt cliff, not knowing what faults or surprises lay hidden inside the rock. As they hammered downward, the floor remained invisible, buried beneath tens of thousands of tons of untouched stone. There was no way to check measurements against a plan or to adjust for mistakes once the trench was started. The excavation advanced in strict sequence. Each layer removed from the summit exposed the next, but only after the stone above had been completely cleared. The crew had to maintain perfect vertical walls as they deepened the trench, or risk collapsing the sides and ruining months of work with a single miscalculation. If the trench drifted even slightly offline, the alignment of the temple's core would be lost. There was zero margin for error. A misplaced cut in the roof or outer wall would mean the entire structure, hundreds of feet below, would never appear as intended. The deeper the trench, the greater the challenge. Air and sunlight faded as the pit grew. The team could not see the temple's final shape as they worked. They carved blind, trusting only their measurements and the memory of the architect's design. At each stage, the geometry of the future bridges and pavilions had to be anticipated long before they were visible. Every support column, every span of solid rock had to be preserved from the very first cut. If a section was accidentally removed or left too thin, it could never be rebuilt. The risk was absolute. Unlike building with blocks, there was no way to patch a mistake. Only by removing material in the exact right sequence could the temple's form emerge, hidden until the last ton of stone was hauled away. Bridges of solid basalt span the gap between Kailasa's main sanctuary and its gatehouse, each one carved in perfect alignment with the rest of the temple. These bridges were never assembled or moved into place. They are continuous with the living rock, preserved from the very first cuts at the summit. To achieve this, the planners had to foresee not just the temple's footprint, but the exact locations of every span and support, years before the finished form would ever appear. Modern architects rely on detailed blueprints, digital models, and survey equipment to coordinate such features. Here, the only tools were string, sight lines, and memory. The challenge goes beyond geometry. Each bridge had to remain structurally sound as the surrounding stone was removed, resisting collapse as the excavation deepened. The margin for error was razor thin. Carve a few inches too far and a bridge would fail, destroying months of labor. Carve too little and the temple's proportions would be thrown off, with no way to reattach or reinforce the stone. The bridges, once isolated from the mountain, had to stand on their own, with no scaffolding and no second chances. Contemporary engineers have run simulations of the bridge alignments and load paths. The verdict is blunt. Even with computer-guided machinery, replicating this feat in hard basalt without visual access to the lower levels would be considered high risk. One civil engineer said they would need a full three-dimensional scan of the mountain before starting, and without that scan, the risk of catastrophic misalignment would be too high. Replicating the same result with CNC equipment and guided systems still demands data that the original builders clearly did not have. No such scan existed in the 8th century. The builders worked blind, yet the bridges align within inches across spans of dozens of feet. Their success is not just a testament to endurance, but to a level of pre-planning and spatial visualization that modern teams struggle to match. The physical evidence of bridges that join temple and gatehouse seamlessly forces a hard question. What planning methods were at work, and why cannot they be replicated today with all our technology? The improbability of this precision points directly to the next forensic challenge. If such planning defies replication, what other traces of method remain in the stone? A forensic question hangs over the plateau. After the removal of hundreds of thousands of tons of basalt, where did the debris go? Modern remote sensing teams have swept the landscape around Kailasa with drone-mounted cameras, high-resolution orthomosaics, and LiDAR scanning. These methods can detect subtle changes in ground elevation, mounds, terraces, or buried dumps down to a fraction of a meter. The search area extends for kilometers in every direction, targeting gullies, riverbanks, and all plausible corridors where spoil could have been dumped or hidden by time. The digital terrain models show the natural slope of the Deccan Trap, punctuated by the carved court of the temple and the outlines of later structures. But nowhere within the survey envelope, no matter how the data is sliced, does a feature appear that could account for even a fraction of the missing rock. There are no massive spoil heaps, no artificial embankments, no infilled valleys that match the expected volume of material. Soil stratigraphy and ground-penetrating radar, where deployed, reveal only thin layers of colluvium and natural sediment. The expected signature of a dump, thick, angular rubble, distinct from river-worn stones or agricultural fill, is simply absent. The result is a negative, a conspicuous lack of evidence. The landscape around Kailasa remains largely undisturbed, with no trace of the enormous debris field that should accompany such an excavation. The fate of the rock is not just unexplained, it is missing from every measurable line of inquiry. The absence stands as its own kind of evidence, sharpening the enigma of how the mountain was carved and what became of what was taken away. In the late 17th century, the Mughal Emperor Aurangzeb turned his attention to the temples of the Deccan. His army, armed with iron tools and imperial orders, came to Ellora with a single aim: to erase the sacred from stone. At Kailasa, legend says 1,000 men worked for 3 years, chipping, prying, and hammering at the basalt walls. Their efforts left scars, mutilated statues, and gouges in the reliefs, but the core of the temple endured. The walls, carved centuries earlier, resisted every blow. Endured. Basalt is no ordinary rock. On the Mohs scale, it rates 6 or 7, harder than steel chisels could reliably cut. The same stone that ancient carvers shaped into elephants and gods proved nearly impervious to Aurangzeb's men. Physical evidence remains: broken trunks, battered faces, and shallow scratches that never breached the surface. The deeper structure stands untouched, a silent rebuke to those who tried to destroy it. Basalt. No Mughal chronicle records the full story. The Persian histories of Aurangzeb's reign mention campaigns and iconoclasm, but they do not record a failed demolition at Ellora. What survives is the material proof, the contrast between ancient mastery and later frustration. The effort required to damage even a fraction of Kailasa hints at the challenge faced by its original builders. If destruction with 17th century iron proved so futile, the question sharpens: what method allowed 8th century hands to excavate and sculpt this mountain? The paradox of the tool marks, small, regular, and precise, now stands in the shadow of a rock that would not yield, not even to an emperor's will. Paradox. Under magnification, the stone of Kailasa reveals a puzzle that numbers alone cannot resolve. Across the temple's vast walls and pillars, the surface is textured with a dense pattern of parallel marks, each roughly 1 inch wide. These shallow grooves run in tight uniform rows, as if etched by a craftsman's steady hand. Photogrammetric surveys confirm the regularity. The marks are strikingly regular, repeating at intervals too precise for random blows. There are no deep gouges or broad scars that would indicate removal of massive chunks of rock. Instead, every visible surface, whether a flat wall or a sculpted elephant, bears the same fine chisel signature, as if the entire mountain had been shaped by thousands of careful measured taps. The contradiction deepens under closer scrutiny. To remove 400,000 tons of basalt, the expected evidence would be wide, aggressive tool marks, signs of bulk excavation, not just finishing. Yet the stone tells a different story. The marks do not widen or deepen near structural transitions, and they do not shift in size from the roughest chord to the most delicate frieze. Experimental archaeology with 8th century iron chisels produces broader, rougher scars, often with splintered edges and inconsistent spacing. At Kailasa, the finishing is relentless and uniform, as if the stone itself resisted all but the smallest, most controlled incisions. No matter where the analysis begins, at the base of a column, the sweep of a bridge, or the shadowed recess of a shrine, the same pattern persists: 1 inch wide, chisel marks, precise and repetitive, without evidence of large-scale breakage. The physical record contradicts the scale of the excavation. The surface of Kailasa is a forensic paradox. An entire mountain removed, but only the smallest marks remain to show how. 3 main hypotheses compete for the title of Kailasa's missing method, each demanding a direct forensic test. The first is legendary. Ancient texts describe weapons or devices, brahmastra or agniastra, that could reduce stone to vapor or to glass. If such a technique was used, the evidence would be locked in the rock itself. Petrographic analysis would reveal signs of vitrification, microscopic glassy textures, melt bubbles, or thermal gradients in the basalt. No spoil to find, but a heat signature left behind. The second line of inquiry is chemistry. Some propose that the builders softened basalt with plant-based or mineral concoctions, allowing the rock to be scooped or scraped away. This theory predicts a chemical residue, unusual elements, or altered mineral phases embedded in the stone. Scanning electron microscopy and energy dispersive X-ray spectroscopy could detect traces of these agents, if any remain after centuries of rain and sun. A positive result would upend everything we know about ancient material science. The third contender is mechanical. The argument here is that large unknown tools, perhaps lost or secret, did the heavy lifting, while the small chisel marks are only finishing touches. The telltale sign would be subsurface macro scars, hidden fractures, percussion cones, or tool chatter beneath the polished surfaces. High-resolution imaging, ground-penetrating radar, or micro-CT scans could expose these buried features and distinguish between manual and mechanized removal. Each theory draws a map for investigation, one testable by rock, another by chemistry, the last by structure. The evidence waits in the stone, ready for those willing to look beyond legend and into the realm of measurable fact. Today, the Kailasa Temple stands as a challenge, not just to historians, but to modern engineers. New technology still fails to explain its creation, and the missing 400,000 tons of basalt remain unaccounted for. Until we bridge the gap between legend and mathematics, the mountain's secret endures, demanding we question what we truly know about our past. What's your theory? Join the conversation below.